welcome to this video. In this video, we're going to start thermal physics. So we're going to take a look at the zeroth law of thermodynamics. Now, the zeroth law is not something that comes up too often, but the zeroth law is something that you will have to know. They won't necessarily refer to it as the zeroth law, but I'm going to give you a little bit of extra information as to how we came to this definition of temperature. So that's exactly what the zeroth law of thermodynamics is. The zeroth law is how we define temperature, and it's called the zeroth law because we had all three laws of thermodynamics well planned out, and then we realized we haven't actually formally defined what temperature actually is. If I asked any of you guys to define to me what a temperature is, it's a pretty hard thing to define. It's kind of just a thing. We know what temperature is, but we couldn't put that explanation into words. So somebody had to do it. And when they did, they came up with the zeroth law of thermodynamics. So they had to go back before the first law and say the zeroth law is this. This is why it's called the zeroth law and not the first law. But what the zeroth law states is if I have three bodies, so body A here, which is just a box full of gas or something like that, and I have body B here, and I have body C here. Now these are all just boxes of gas. So this is just a system A, system B, and a system C. Now it states that if A is in thermal equilibrium, I'm going to simplify equilibrium to just EQ, with B. Now thermal equilibrium meaning that there's no transfer of heat energy, so there's no heat flow. So usually if we put a hot system next to a cold system, we'll get some heat transferred from the hot to the cold, because that's how the second law of thermodynamics states it should be. If we have thermal equilibrium, it means that we actually get no heat transfer. So these things are both at the same temperature, so there's no temperature gradient for the heat to be transferred across, because they are still exactly the same. They'll just maintain their original temperature. But if A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then this means that A must be in thermal equilibrium with C, okay, even though they aren't touching. So if I made a bridge here that I can allow heat to cross, there would be no heat transfer between A and B. If I did the same for B and C, there's no heat transfer here, which means actually if I were to get rid of this system, B in the middle, and did this, there would be no heat transfer between the two. This basically then leads on to the fact that you don't have to have things in contact for them to be at the same temperature, thus defining what a temperature is. We allow a temperature to be any state where two of these things would be in thermal equilibrium. Then we need to define a 0 point for this scale, and we need to come up with some sort of scale. So the first person to do this was Fahrenheit. So he came up with the first temperature scale, so temperature scales. The first one was Fahrenheit, and Fahrenheit said that his temperature scale is going to be based off of his internal body temperature. Okay, now this is not a good method, because only he has that internal body temperature, and his internal body temperature can change, which means that he has set a 0 that's not actually going to be a definite 0, depending on what time of the day he's measuring it, what he's eaten, if he's ill or not. His body temperature is going to change. It's never going to be set to be an exact value. So then this isn't something that we use. This is still used in America quite a bit, but it's not exactly the best temperature scale, which is why then Celsius came along and made a separate scale that is based on the water. So it's based on the freezing point, so the melting point, and the boiling point of water. And he said that 0 degrees Celsius is the melting point of water, and 100 degrees Celsius is the boiling point of water, and therefore I'm going to have 100 degrees Celsius difference between these, and I'm going to continue with this scale. And this is the scale that most of us will know from everyday use. But then we said that we'll find out by experiment, we find that actually there's a second zero that works for everything. So water, again, under different pressures could have different melting points. So this is under standard conditions, meaning standard pressure, standard temperature, room temperature, or 0 degrees Celsius. But then if I were to then change the pressure, I'm changing the melting point and boiling point of water. So we came up with a third scale, and this is what we call the absolute scale of temperature, because it's based on the absolute zero. So absolute zero, just to define formally what absolute zero is, this is the minimum temperature. So this is the smallest possible temperature anything can get to, where there is minimal energy. Now, there's not completely zero energy. There will still be energy present. As we learn in particle physics, anything with mass will have energy. So the mass just doesn't disappear when you reach absolute zero. It just means that it will be in a state where it will have basically zero kinetic energy. It will still have some potential energy based on where it is in the system, and so on. Okay, and absolute zero, in terms of the Celsius scale, we say that 0 Kelvin, so this is the smallest possible temperature we can ever get, is the same as minus 273 degrees Celsius. Okay, and this is a good conversion to know. So in order to get from degrees Celsius to Kelvin, which is what you'll have to do most of the time, you just minus 273. Okay, and therefore to go the other way, you would just add 273. Now, the Kelvin scale is probably the most important temperature scale. This is what every single temperature you have in any equation in physics always has to be in. So this is our SI unit for temperature, now formally defined as to where it came from. So we have these temperature scales. We will always look at Kelvin, because Kelvin is actually directly proportional to the energy that something has. And we'll find out as we go through thermodynamics that actually the energy of a system can just be represented by the temperature of the system. And so if we have Kelvin increasing, it must mean that the energy is also increasing. So therefore, the temperature scale of Kelvin is kind of a scale of just the energy and how it changes. Thank you for watching.